All right, so we're able now to identify the shapes of our compounds by looking at them, right? We have a water molecule here, for example. We can use as a little review. The chemical formula H2O, we draw the Lewis dot structure. It looks like an oxygen bound to two hydrogens, right, with two regions of electron density that are non-bonding, four regions altogether. What is the shape of this molecule?
Water, I remember, is bent.
Okay, but if you didn't remember, what's the shape of water? Right? What's the overall shape of the four regions of electron density? What shape is that?
Oh, four regions?
Yeah.
That's tetrahedral.
Very good. Tetrahedral. So what is the angle between these two bonds here?
Well, it's 109.5, but you said that the lone pairs kind of squish the other ones together, so we say a little less than 109.5?
Very good. A little less than 109.5. And the answer is actually 104.5. So, this number isn't important to remember, but it's important to recognize that the tetrahedral got us to the correct angle and a little less than that correct angle because we have lone pairs squeezing those two bonding hydrogens close together. Good. Okay, which requires more space? Bonding pairs, lone pairs, or both of the same?
This is what you just said. It's the non-bonding or the lone pairs which require more space.
Very good. Excellent. And how about this one? What's the geometry of SO2?
SO2. I guess we got to draw it, right?
That's right. You always have to draw the Lewis dot structure. So if you haven't remembered how to draw Lewis dot structures, you should go back to the videos from the last chapter titled Lewis structures and go through them and make sure that you can draw Lewis dot structures. Very important. So we're going to draw Lewis dot structures. Central atom, is it sulfur?
Yeah.
And for those of you at home, if you think you know how to draw Lewis dot structures, why don't you go ahead and draw this one first and then see how it compares to ours. Okay? So hopefully you had a chance to try it. Sulfur going to bond to oxygens.
Yeah. And then you have 18 electrons.
18, what do you mean?
18 valence electrons.
Okay, where did you get that 18?
Oxygen had 6 each and sulfur had 6. So 6 times 3 is 18.
All right, now how did you know that?
Because the sulfur and oxygen are both in row 6.
Very good. So that row told us the number of valence electrons each one had, and the resulting 18 electrons are the number of valence electrons that we start with. 1, 2, 3, 4 valence electrons are already on the board in our skeleton molecule, so we have 14 valence electrons left. What are we going to do there?
Put some on sulfur.
All right, I'm going to put some on sulfur. 1, 2, 3, 4. Is that good?
Yeah, that's good. Now try some on oxygen.
So I'm going to make sure I don't lose my accounting here. 10 left. All right. 1, 2, 3, 4. Is it okay if I go like this? 5, 6, 7, 8?
Yeah, that's a good idea because sometimes you need to do that.
Now let's see. Did I put too many electrons on?
I don't think so. I think we still just have 2 more. Let's see. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, so we have 2 more to put on.
All right, so where should we put them?
Let's just put them on, well, if we put them on one of the oxygens, then we're not going to have enough on the other oxygen. Let's make them into a double bond.
Okay, like that?
Yeah, and then take the other electrons on top of the sulfur and make another double bond.
All right. You're getting pretty good at this, Fred.
Yeah, I've been practicing.
Good. Good for you. So, now, back to the question, what's the geometry of this molecule?
3 regions of electron density.
Very good. 3 regions. 1, 2, 3. So regardless of how I drew it, central atom with 3 regions of electron density is going to have what kind of an angle there?
120.
Do you remember the name of that?
That's trigonal, but it's all in the same plane, so trigonal planar.
Is that the shape of this?
No, that's just the shape of the 3 regions of electron density.
That's right. This is trigonal planar. But this one here, its shape is what?
Well, if you take that shape and make one a lone pair.
I mean like this?
Yeah, then the rest is just bent.
Very good. Just bent. With an angle here of, what did we say, about 120, maybe a little bit less?
Yeah.
Very good. Excellent job. Okay. What's the molecular geometry of the electron domains around the carbon in CH4?
This one's pretty easy.
Yeah, okay. Well, then tell us. Well, maybe we should let the folks at home work on it.
Yeah.
All right, so they've had a chance now. They pushed pause. They thought about it. What is it?
It's tetrahedral.
Very good. So for CH4, we might not be familiar with it, but we've worked on it a lot. So hopefully we kind of recognize that our shape right here, our Lewis dot structure, CH4, that's going to be a tetrahedral molecule. What's the angle between the carbon-hydrogen bonds, two of the carbon-hydrogen bonds?
109.5.
That's right, 109.5. Good. All right, so just like you can have polar bonds, you can have polar molecules. Now remember how we could identify whether a bond was polar or not?
Kind of.
So tell me, is this kind of a bond polar?
Yeah, because fluorine is very electronegative and hydrogen is not.
Very good. And so we kind of would either draw the electron density around the fluorine, something like that, or we could use our delta negative and our delta positive to kind of show somebody that there's an imbalance of the electron density. Now, why is this again? Why is it when you have a hydrogen bound to a fluorine, there's an imbalance?
Fluorine wants to hog the electron density. Doesn't share very good.
Very good. Excellent job. If in a compound you have this kind of polar bonds, so for example, water has two bonds, two hydrogens bonding with this oxygen. Each of them is a polar bond. And so your electron density is coming up towards this oxygen. And the result is the whole molecule becomes polar, with more electron density on the top where the oxygen is and less electron density down below where the hydrogens are. Same thing with the compound ammonia. Its shape here is trigonal pyramidal, and the nitrogen on top pulls the electron density from the hydrogens, so the result is a polar molecule. To have a polar molecule, you need to have some polar bonds, but you also need to have some asymmetric shape. For example, if you have this bond or this compound right here, carbon dioxide, carbon-oxygen bond here in carbon dioxide, two of them are polar. However, they're pulling electron density back against each other, and the result is no net polarity. And so the molecule ends up being nonpolar. BCl3, same thing. Even though you have some polar bonds here, the result is a nonpolar compound because it's not asymmetric. It's very symmetrical. Okay? Another example over here. So, to be a polar molecule, you need to have asymmetry and you need to have a polar bond. So, what do you think? Polar or nonpolar? This molecule here has some oxygens down here, carbons over there.
The oxygen's electronegative.
Very good. The oxygen's electronegative, so the electron density is going to want to reside around here or around here. Does that look symmetric?
No. So I would say that's polar.
Very good. It is polar. How about this one over here?
That's a phosphorus on top?
Yep. Phosphorus here. Chlorines down here.
Is phosphorus and chlorine, is that a polar bond?
Well, let's see if we can look at our thing here. Periodic table. Which one's more electronegative? Phosphorus or chlorine?
Electronegativity goes to the right and to up, right?
Yeah.
So chlorine would have more electronegativity.
Okay. Is this a symmetric molecule?
Well, it's symmetric if you think about the middle and spinning it, but top to bottom, no. It's kind of trigonal pyramidal, right?
That's right. It's trigonal pyramidal, so this is the top of the pyramid. and the electron density is flowing down towards the bottom. So this would be a polar molecule as well. How about this one here?
What are those gray ones?
These are carbon,
And the white ones?
hydrogens. Does it look symmetrical or asymmetrical?
I think it's symmetric.
It is. It's symmetric. Are carbon-hydrogen bonds polar?
I don't know.
Well, carbon-hydrogen bonds are only minimally polar, not much polarity there. And because this is symmetric, you'd have to say that this is not a polar compound. Okay. Another thing that you'll see is looking at larger molecules and needing to recognize polar parts of larger molecules and nonpolar portions of larger molecules. For example, each one of these bends here represents a carbon, and these are oxygens within this molecule. This molecule is symmetric. However, there are what we call, because it's so big, we call certain regions of it polar. So you could say that this region right here, because of the oxygens, are polar, but these regions over here would be considered nonpolar regions. All right? So polarity is some molecules, larger ones especially biomolecules. There are sections which are polar and sections which are nonpolar, but the whole compound itself, you know, it could or could not be polar, but it's usually you're looking at smaller sections on a larger molecule anyway. Okay, good. So that's a good place to stop. We'll talk about this next time.